Hello everyone, my name is Chao Peng, comes from Institute of Information Engineering, Chinese Academy of Sciences. Today I will be sharing our work named Advancing Binary Code Similarity Detection via Context, Content Fusion, and LLM Verification. Binary code similarity detection is a technique assessing the similarity between two binary code snips, with application in vulnerability detection, malware clustering, and pattern analysis. BCSD approaches have evolved from rule-based to learning-based methods. Their pipeline begins by extracting features from binary code and then converts these features into embeddings through the neural network model. Next, the similarities between the query function and the candidate functions are computed for ranking. Finally, analysts will manually review the remaining candidates to identify the target function. Despite recent advances, learning-based business approaches face two main limitations. First, achieving both high precision and recall in large-scale detection is difficult. As the number of candidate function grows, so does the number of invariant ones with similar features, forcing analysts into a trade-off. A stricter filtering may miss true positives, while looser filtering leads to more false positives. Second, this method lack of interpretability, outputting only embeddings and similarity scores that are obvious to humans. Uh, Analysts must manually verify candidates, which is time-consuming and error-prone. We take two function pairs to motivate our method. A1 and B1 are compiled from the different source code, while existing business esteem approaches show high similarity scores due to their similar code and structures. In contrast, A2 and B2 compile from the same source code, while BSSD approaches show low similarity scores due to the code changes after compilation. By constructing the dependency graph of the two function pairs, we found that it offers a valuable alternative perspective for evaluating code similarity. We name it as the function context. The orange part refers to the common error between two dependency graphs. As can be seen from the context view, we can easily identify the relationship between the function pairs. Unfortunately, function context alone is not a complete solution for error handling. Function pair A3 and B3, despite exhibiting high content and context similarities, are oriented from different source code, leading to a false positive. In such cases, large language models offer a promising solution, as shown in Figure 2. The large language model analyzes and generalizes the code logic of the two functions, ultimately determining they do not orientate from the same source. Considering the strength of the context, content, and the LLM, our key idea is to combine the strengths of them to balance detection accuracy and efficiency. We propose call a context content fusion and LLM verification. The workflow has two stages, a candidate retrieval and LLM verification. In the first stage, context and content similarities are computed separately. They fused using a weight alpha to rank candidates. The top kick most similar functions are selected for the next stage. In the second stage, the code of the query and candidate functions is extracted, and an IRM is used to verify whether the candidates match the target, providing explanations. The experiments use the bin kit to create two datasets, D1 and D2. The experiments include subtests with different compilations, such as cross-architectures and cross-compiler optimization levels. We select five SOTA works as our baselines, evaluating using the metrics like MR, precision recall, and F2 scores. Our LLMs cover three types, including general, task-specific, and reasoning models. The LLM settings including the combination of the two main parameters, TOPI and temperature. We also construct 60 different promotes to show how promote technique affects the LLM performance, including their shoot, few shoot, critical, and three variants of train of thoughts. Our first research question explores the impact of context on candidate retrieval. Table 1 shows that adding context will improve the ML score by a large margin. Specifically, using Hermes with context requires the majority of target functions within the top 5 candidates, significantly reducing the LLM processing costs. The ablation study in Figure 1 shows that the base method with context outperforms other configurations, while other configurations using incomplete context will result in a 11% to 14% drops, highlighting their importance. We identified 4 key findings when evaluating the impact of different promoting techniques on LLMs. Model size, the first finding is model size significantly affect the accuracy and sensitivity to prompts, but the effect diminishes as the model grows. Promoting techniques have varying impacts. For example, few shot is the most reliable across all models. COT Pro generally outperforms COT Lite. COT Self works better for large or reasoning-oriented models, and the critical often underperformance even below their shoot learning. Third, general purpose LLMs outperform task-specific or reasoning-oriented models in overall performance. Fourth, the LLM settings have little impact on the classification results. These findings suggest optimal performance requires a balance of model size, promoting technique, and model type. To evaluate the LLM-generated explanations, we randomly select 50 samples from the D2 dataset and divided 6 participants into 2 groups. In the utility study, Group 1 received only code snips, while Group 2 received both code and LLM explanations. In the reasonability study, Group 1 assessed the reasonability of 700 explanations. The results show that LLM-generated explanations are practical and reasonable, which can improve the manual verification efficiency and accuracy. For the final research questions, we evaluate Corfu in the BCSD test. Compared to using Hermes alone, Corfu, which integrates Hermes context and DeepSeek V3, greatly improves the precision and recall. In contrast, Corfu only requires a few extra time and money costs. For example, the time cost increased only by 3% and $6.6 for 10 million function pairs, which is a large BCSD detection. Thus, Corfu is a practical solution for the BCSD task. That's all. Thank you.